PVC and other types. Here you can see different types of plastic piping. It divides into the flexible piping. It doesn't require the stress analysis because it's self-compensated. We don't need to perform flexibility analysis for such type of piping. Also, there are reinforced plastic piping with different type of reinforcement. Like here, you can see the metallic with some metallic wires. We also will not perform such type of analysis using this model of PE, PVC, PVP analysis, because this type of piping is better to analyze using the code for fiberglass piping, FRP, GRP, and other, using the ISO 14682. 92. So we will analyze the rigid piping that is made from the polyethylene, polyvinyl chloride, polypropylene, and other materials without reinforcement and not flexible. So what is the main features of thermoplastic piping? Unlike the steel piping, it is the allowable stress. It depends on the service life and temperature. For example, for steel piping, the allowable stress doesn't depend on service life. Another feature is the thermal expansion for plastic piping is several times, about 20 times greater than for the steel piping. So the thermal expansions is very important for the thermoplastic piping. Also, linear expansion from pressure load, also very great. So we always should consider the Bourdon effect for the plastic piping. The Bourdon effect is elongation of the pipe under the pressure, from the pressure load. So sometimes we should take into account the swelling elongation. It's caused by the chemical reaction between the pipe material and the product. Also, the Young models, it's creep models, depends on the service life, temperature. For example, for steel piping, the elastic models doesn't depend on the service life, but for plastic piping, it depends. Santosh, please switch off the microphones for those who are not speaking, okay? Another feature in operating condition, the average creep models is used. And Poisson ratio also depend on the temperature. For example, in the steel piping, the Poisson ratio is the same for all temperatures, but for plastic piping, the Poisson ratio changes upon the temperature. So we have to use it in the database, add it in database for different temperatures. And also the allowable stress for plastic piping depends on chemical resistance factor, which we also should consider. Here you can see the user interface of the START-PROF software, and here is the properties of the pipe element. And here you can see that we can just select the some type of thermoplastic material. The analysis is performed according to the DVS code. It is DVS 2205, 2210, and also European code. START-PROF perform analysis using this code, and material properties are taken from this code and this code. So these two codes is used for material properties calculation, and this code is used for stress analysis. Here you can see the PVC piping and failure of such piping. You see the crack on the PVC piping, and here we have some small video. Let me reduce the volume. This is the failure of the PVC pipe and the pipe from PVC material. Let me run again. So which load caused this crack? The investigation shows that the torsion moment caused this type of failure. We modeled this in START-PROF. This is the PVC-C type 2 material. We modeled this line. Actually, it was designed without any stress analysis. And after the performed stress analysis, START-PROF shows that this line should fail, and almost in the same place the START-PROF showed it failed. Okay, so this is another failure, very long polyethylene pipe PE 100. Actually, there is no problem with the stresses. There is no cracks, but there is a problem with supports. When they analyzed this piping, we received the great displacements of this pipe in lateral direction, and the displacement was about 0.5 meters. And at some locations it was 1 meter, so very huge lateral displacements, and this caused the problem with supports. As you can see, it was on that type of simple supports, and that supports was not designed to withstand so great lateral displacements, so it turned over. As you can see, this is the support. It turned over at some locations, and the sad thing is that that supports are moving depending on the outside temperature. So when it cooling down, it moves there. When it warm up, it goes there, and it always moving in both directions several times per year for the maximum displacement at 1 meter. So this is the problem. It should be redesigned. All supports should be changed to another one. This shows why we should perform the stress analysis of thermoplastic piping systems. So sometimes we can have cracks, sometimes we can have great displacements, maybe sometimes we have great loads on the supports, on equipment, and so on. Actually, the DVS 2210 code is designed for very simple calculations. It was designed for manual calculations, for simple forms of the piping. It is L loop, Z loop, and U loop. But START-PROF extended the capabilities of this code, and it allows to perform any complex configuration of the piping system, like you can see on the picture here. This is another example. It is the polyethylene 100 ship ballasting system analysis. It's piping on the ship desk, and it also take into account the hog and sack deformations of ship desk. Everything was performed in START-PROF. This is another piping system made of the polyethylene 100. It's a process piping system. Actually, if we'll check the DVS code 2210, we can compare it with the START-PROF analysis method. For example, DVS required to take into account the thermal expansion. START-PROF do this analysis. As you can see here, we consider the thermal expansion. This is the epsilon 1 deformation. The second deformation is caused by the Bourdon effect. It's elongation due to pressure load. Also, it is required by the DVS code. And the third deformation is a chemical swelling effect. And it also can be performed by START-PROF. For example, in START-PROF, additional properties of the pipe, you can define the swelling strain value here. Also, you can take into account the special factor for the thermal expansion. It take into account the nonlinear distribution of the axial strain caused by the thermal expansions through the wall thickness of the pipe. Sometimes we should take into account. So here it is just a factor for the axial strain from the thermal expansion. And you can define this value here. If you will use a 1.0 value, it will use just full thermal expansion. Also, as I said before, in contrast to DVS code, START-PROF allows to analyze any complex piping layout. And also, the DVS code says that it was designed for simple LZ and U loops, but for more complex system, we should use the special personal computer calculation programs like START-PROF. And also how we can determine the allowable stresses. So the allowable stresses determined according to the DVS 2205 code and also EN code 1770H. And if we will check this code, let me show you. Okay, and also you can find that curves from that code in the Simona engineering guide. Simona is a company that it's manufacturer of plastic piping systems, and also you someone mute me. Okay, so Simona engineering guide allows you to determine the creep models for different type of thermoplastic materials. And as I said before, the allowable stresses are taken from DVS 2205 and EN code. And also the special feature of this of thermoplastic material is that we should use different service life for elastic models. For example, if we perform analysis from primary and secondary operating loads, we use the elastic modulus at ambient temperature and operating temperature and use average value. And also, if we perform analysis for occasional loads, for example, occasional loads, wind, seismic, water hammer, slug flow, and other occasional loads, we should use the creep modulus at ambient temperature and operating temperature for the service life 0.1 hour. But if we analyze operating mode, we should use the full service life, for example, 50 years. And also, if we calculate the loads on the supports, in this case, we should use the creep models at the service life of 100 minutes. So the elastic models depends on which load case we're using. For load cases to determine stresses, we use full service life. For load cases in which we determine the support loads, we use 100 minutes elastic models, and for load cases for occasional loads, we use 0.1 hour service life. So we use different values of elastic models. Also, the thermal expansion factor, also taken, for example, from the Simon engineering manual or the DVS code, and also the Poisson ratio. Let me show you. The Poisson ratio also depends on the temperature. So, for example, this is PPH material. For 20 degrees, it is 0.30 H, but for 50 degrees and greater, it is 0.5 Poisson ratio. So Poisson ratio depends on the temperature. And also for stress calculation, allowable stress calculation, they use that curves. For example, this curve is taken from EN 177H. And these curves consist of two parts. This is the first part and the second part. And here you can see this is the first part, second part, and each part can be described using this characteristic equation. And here we should substitute some parameters. We have 4 parameters what they should define here in the database of the material. So this is the material database in START-PROF for thermoplastic piping. Okay. For example, we can use DIN code, this one, and the curves are the same as in European code and as in DVS code, but in this code you can find the values of these parameters for this characteristic equation, this one. And if we substitute that parameters, we will receive that curves for allowable stresses. So here you see the same values as in this code. Okay, so START-PROF are just taken that parameters from the DIN, and the same is European code and the same in DVS code. And also for actually the DVS code doesn't contain anything about the T and bend calculation. So START-PROF used the following equations for stress intensification factor, stress for bands, T elements, and also for flexibility of the bands. And also actually for the thermoplastic piping, we also should perform the buckling checks. START-PROF doesn't perform such analysis right now. Maybe we'll add this in next versions, but right now it doesn't perform such analysis, so you have to do this manually. For example, you can find here the equations how to do such analysis. It's internal negative pressure or external pressure analysis for buckling. So you have to do this manually. And also, if you have the allowable stress values and you want to determine the parameters of this characteristic equation, we have a special Excel file that allows you to do this. You just need to define 3 points. For each point, you define temperature, service life, and allowable stresses. And if you will fill this table for 3 points, START-PROF, sorry, not START-PROF, it's Excel file will give you the values of that characteristic equation. We did this because some our customers required to define the custom values of that parameters. So we just did this Excel file. Let me show you. This is the Excel file. So here you can just define some values and you will receive the factors of characteristic equation. So how you perform analysis? Let me just show you some simple piping system I will create it from the scratch. For example, here in START-PROF, I select the DVS code for thermoplastic material. I define ambient temperature, for example, it will be 10 degrees. Okay, and just draw your piping system. I create the pipe element, define the properties. For example, length will be 30 meters, diameter, for example, like this, the wall thickness. I just use random values. Here you can define the type of material, for example, PVC. It is taken from the database, but you can add your own materials into this database. So I will just select the PVC, just define some pressure, for example, 2 atmospheres, the temperature, for example, 50 degrees, the insulation weight, fluid weight. Let me add some fluid weight. It will be water, just fresh water. And additional parameters here you can define some factors. Let me use 1.0 value. This is the swell and strain. I will not define any swell and strain. And some other parameters I will just use 1.0 for all values. Click OK. And now just draw the piping system the same as we do for the steel piping. I add anchors. I will add some expansion loop in the middle, like this, maybe 2 by 2 meters, like this. Some expansion loop. I will add the bands. Let me add the band. We have meter band and forged elbow. I will use forged elbow, for example, radius about 300 millimeters, the wall thickness, and some other parameters. I will just copy this band here, and here I will just use Ctrl V. Okay, so I copy this band and add supports. Let me just insert multiple nodes. I will use rest and support, for example, 10 rest and supports here and here, and I will add support here, rest and support. So we have some simple piping system. Let me save the file. Okay, so now just run analysis. Of course, you can define several operation modes, different load cases with different temperatures, different pressures. Right now, we have just one operating mode. And here you can see 4 load cases that is hidden inside this operating mode. And we can see analysis results. For example, it is piping stresses. I will select the operating mode, and here you can see the stress from primary loads. It is the weight plus pressure loads. This is the stresses from primary and secondary loads in hot state. It is weight, pressure, and thermal expansions, and also support movements and other secondary loads, and also cold state. This is also weight, pressure, and temperature, but after that we cool down our piping system, so -T, and all friction forces working in the reverse direction, so all friction force reversed, and pipe returned back to original installation state. So this is the cold state. And here you can see the stress values. This is the allowable stress. It depends on the temperature, depends on the service life, and also this is another allowable for primary and secondary loads, and here is for the allowable for the cold state, and this is the calculated stresses in this piping system. Also you can see stress in elbows. If we'll add T elements, you will also see stresses in T elements. And of course you can see the restrained loads, support loads for the anchors. Here is the anchor. And also you can see the animation of the deformations like this. So this is the thermal expansions. As I said, the thermoplastic material has the huge thermal expansions. For example, if I will select this node, you will see the elongation along the x-axis is about 32 millimeters. So it's much greater than for steel piping system. And also this material is, the elastic modulus is much lower than for steel piping, so we have to put more resting supports. As you can see here, we have deformations from the weight. So it is moving down from the weight loads, okay? And let me open the presentation. And also we performed the test comparison between the examples in the Simon engineering guide, this one, Simon engineering guide. And we calculated the allowable stresses using Simon engineering guide and created the same model in START-PROF and compare the stresses, so you can see it is the same. And actually in START-PROF it's more accurate than in example in Simon, because START-PROF calculated using equation, but Simon engineers just took the stress from the graph. And you see here allowable stress is also the same as in Simon engineering guide. And the example 2, actually the difference is a little bit greater, but actually START-PROF, I double checked it, and START-PROF has more accurate values than in Simon example. If you will calculate it more accurately, I calculated using the Excel, and it is more accurate than this value. So this is more correct value. And also the let me check wall thickness. We had the wall thickness calculation in START-PROF. Let me show you. If you will select File, New, all elements, select the DVS code, and here you can calculate the wall thickness of the pipe, for example, 200 millimeters, 40 degrees, define the factor values, define the material, for example, PE 80, service life, for example, 50 years, define pressure. You can calculate the wall thickness of this pipe. So I compared the values of the wall thickness in START-PROF and example in Simon engineering guide, and I found that Simon engineering guide has a mistake. It has incorrect value of the wall thickness calculated. I don't know why. Maybe the engineers from Simona did a mistake, but I'm sure that START-PROF value is correct. I checked it several times, so this is just a mistake in Simon Engineering Guide. And also we use the special factor for secondary loads. When we calculate stresses from secondary loads, START-PROF use the special factor for the allowable stresses. That's why allowable stresses from secondary loads, it's a little bit greater than for primary loads. So also START-PROF perform analysis for fiberglass piping. Let me show you. This is FRP piping systems. Let me quickly explain how START-PROF analyze it. So what is the FRP? It is some material, for example, it consists of polymer matrix and reinforced with fibers. Like you can see the manufacturing process of such piping systems and components. And the main feature is that the properties of this material is non-isotropic, it's orthotropic. So we have two elastic models in different directions. We have axial elastic models and hoop elastic models. And also we have two Poisson ratios. It's axial and hoop Poisson ratio. In the database, START-PROF database, you can find the values of elastic models, of axial and hoop elastic models, also the shear models, for example, for torsion moment analysis, and Poisson ratio, expansion factor, and so on. It depending on the temperature. So START-PROF already has some database with material properties, but of course you can add your own materials in this database. Let me show you. For example, now we have thermoplastic analysis. Let me show you database. This is database material library. You open it. This is the plastic material. We have also the steel material to model the steel pipes with plastic pipes in the same model. But let me show you, for example, polyethylene 100. If I click show, you see the properties of this material. This is the characteristic equations, the coefficients for characteristic equation, left curve and right curve, safety factors depending on temperature. This is for the factor for self-balanced loads, for secondary loads. Also, we have expansion factor, Poisson ratio depending on temperature, and creep models. Creep models depending on the service life. This is service life in hours, 0.1 hour, 1.6 hours, 100 hours, and so on. This is the 50 years. And also it depends on the stress value. This is the stress value in kilogram per square centimeter, but of course you can change units to any other one. And here is the stress. So creep models depends also on stresses, and also it depends on temperature. So here you define the values. That values are taken from Simon Engineering Guide. This is the database properties for plastic material, but if you will switch to ISO for fiberglass piping analysis, let me select Vevistron, Future Pipe Industries. I click show, you see the different database with properties of FRP material, and all properties depend on the temperature. Here you see the elastic models, axial elastic models, hoop elastic models, shear models, Poisson ratio. Actually, it is the same for all temperatures. and some other parameters. Let me explain it a little bit later. So here is the main equations for stress analysis of orthotropic material. This is dependence of the shear modulus from the axial modulus and Poisson ratio. And this is the dependence of elastic modulus from the Poisson ratios. And this is the axial and hoop strain equations. Actually, we use it to calculate the Bourdon effect in FRP piping from the internal pressure. So here you can see the strain for unrestrained pipe. This is the axial elongation of unrestrained pipe, and this is the axial tensile stress in restrained pipe from the pressure load and thermal expansion for orthotropic material. So this is the restrained pipe, and all required values are taken from START-PROF database. Another feature of FRP piping is that it has the reinforced wall thickness and special protective layers. For example, this is reinforced wall thickness with fibers. So here we have fibers in this part. This is the wall thickness of FRP material. Here we have fibers like this, several fibers. But this layer, this one and this one, it is protective layer. It doesn't contain any fibers, but it is used to protect fibers from some influences from inside the pipe and from outside the pipe. It's just protective layers, and we don't take into account the protective layers when calculating stresses in the FRP piping systems. For example, in START-PROF, you can define the protective layers. Let me save the model. I will close it. And let me now create the FRP model. I will select ISO code to 2017 edition. I will create the pipe, for example, the same 30 meters, just some diameter, some wall thickness. And here you see the linear thickness and top coat thickness. It is the protective layers. So that layers are not taken into account when we calculate stresses in the pipe, but it's taken into account for example, to calculate the weight of this material and so on. So START-PROF just subtract the linear and top coat thickness from the wall thickness of the pipe. Okay. So how to check the stresses in FRP material? We should use the special failure envelope. For example, here we see the hoop stress in horizontal direction, and in vertical direction we have the axial stress. How to determine if our pipe will withstand the loads or not? So we have to put at least 2 points on this envelope. The first point is 2, 1 point, and the second point at 0, 1 point. So this point means that we have 0 hoop stress, so 0 pressure. Pressure is 0, and we have some axial loading. Let me show you. So this point means that we have some pipe with 0 pressure and applied some axial load on it, and we should determine how great stress this pipe can withstand under axial load. And if we will determine this, we can specify the value of axial stress, allowable axial stress for this point. And another point, it is the pipe under the internal pressure without any axial load. But the axial load actually produced by the pressure, the pressure acting on the end caps of this pipe here, and we have some axial load caused by the pressure. So axial stress usually equal to the half of the hoop stress in such points. So that's why it's called R2. It is the ratio between the axial stress and hoop stress. Okay. Sorry, hoop stress divided by axial stress. So if we perform two tests, the first test and the second test, we can define the 2 points, and this is enough to perform analysis of such type of FRP pipe. And actually, we can use this method, for example, to analyze the reinforced thermoplastic piping. Sometimes we have, for example, polyethylene piping, but reinforced with some kind of fibers, maybe some steel wires or another type of reinforcement. So if you will perform that 2 tests, you can analyze this type of piping using the code for FRP piping systems. And also we can have the third point, but actually I never seen that any manufacturer provide this value. Usually manufacturers provide only 2 points, this one and this one. And START-PROF also applies some additional safety factors for this failure envelope. You can find the detailed description in the ISO code. I will not explain it right now. I have a special training course, online video training course on the stress analysis on the udemy.com, and there I explained it in more details. I will not explain everything in this webinar because we don't have enough time for that. And this is the failure envelope. This is the main equation for this failure envelope, but we just cut. Actually, it is a curve like this, but we cut it into straight lines. Okay. And this is the failure envelopes from the Future Pipe Industries company, and for very strong pipes with different winding angles. 55 degrees, 63 degrees, and 73 degrees. And of course, that values are already included into START-PROF. Here you can see the very strong and also some other manufacturers of the FRP piping system. So let me show you. You just define the material, for example, this one. You define pressure, for example, 2 kilograms. You define temperature, some fluid weight, for example, fresh water, some additional properties, for example, chemical resistance. I will just use 1.0 value. Click OK, and do the same things. Just add anchors, just add the expansion loop. I will add the node expansion loop. This one, 2 by 2 meters, 90 degrees, and add the bands. So we have meter band and forged elbow. So we'll use this type of band, smooth band, not meter band, and copy it here. And also add several supports, resting support, the same as we did for thermoplastic material. Okay, and also let me add support here. Okay, our model is ready. Let me save it. Okay, and run analysis. So now, of course, we can see the animation of the deformed shape of this piping. We can check the support loads, we can check the stresses from primary loads, primary and secondary loads in hot and cold state. So everything that is required by the code. And in STAR-PROF database, you should define the values of the points of this envelope. So this is AL01. It is this point, and the two values, it is this point. It's axial stress and hoop stress, this one and this one. And also we can have the third point. Sometimes maybe manufacturers can provide you the third point values. In this case, you can enter some values here, but actually I didn't see if any manufacturer provide this value. And also it explained the that values where we should take them. Okay. And also we have some additional parameters, some factors that take into account, for example, A0, material degradation upon a time. It depends on the service life, T, and GXX factor. And this GXX factor is also stored in STAR-PROF database. Here you can find that GXX factor depending on the temperature of the pipe. So for example, if you have several operating modes and different temperatures, Vista and this one, you can define different operating modes, and STAR-PROF will use the properties from this database for each operating mode. For each operating mode, the elastic modulus, failure envelope will be different. Here is the table where we can take this JXX factor. And also it take into account the chemical resistance, A2 factor. And also STAR-PROF take into account the A3 factor that depends on the takes into account the fatigue failure of the 4P material according to the equations from the ISO code, as you can see here. This is the equation for A3 factor. STAR-PROF calculate this factor automatically. And to calculate this factor, we should define the FC factor, and this FC factor also stored in STAR-PROF database for materials. So all properties of material stored in the database, so you have to just select the correct material from the database and then perform analysis. If you have some manufacturer that is not included in STAR-PROF database, you can ask manufacturer to provide the properties of this material, and then you should enter them in the database manually, and after that you can perform analysis. Or you can just provide this table for the manufacturer, and manufacturers should fill this table with the data for their pipes, and after that you will be able to perform the stress analysis of such piping system. Also, there is a F2 factor for the failure envelope, and depends on type of loading. For example, for primary loads, it's weight and pressure, we use 0.67 factor. For primary and secondary loads, and for hot and cold state, we should use 0.83 factor, and STAR-PROF do this automatically. And also, if you will define some occasional loads, for example, wind loads, seismic, and some other occasional loads, in this case, STAR-PROF will automatically use 0.89 factor as required by per the ISO code for fiberglass piping systems. And in the stress table, you see, for example, for primary loads, you will see the hoop stress, and corresponding allowable stress. For example, you have a point somewhere here. If this point is inside the failure envelope, it means that the strength of our pipe is okay. But if this point is outside of the failure envelope, it means that we have failure. So, for example, we have point here. In this case, you can see the hoop stress. This is the hoop stress. So you see this value and the allowable hoop stress value, this one. And also you see axle value, this one, and allowable axle value, this one, this point. So here you see the explanation, which values you see here. This point is here and here, and this point is this value, and this point is this value. Okay, so the same idea is used for all other loadings. And how START-PROF calculates stresses in FRP piping? It used the equations from the ISO code. For example, this is the hoop stress, and also for the hoop stress, we also should take additional stress caused by the ring bending effect. For example, if this is buried piping, the soil acting on this pipe and ovalize it, and we have some additional stress caused by the wall thickness bending. And START-PROF calculate this value automatically. Actually, ISO code has a reference for the FVVA code M45, where we have some simple equation that is used for manual calculation of that stresses, but it is very simple, and it doesn't take into account many effects like nonlinear effect or the pressure stiffening. It doesn't take into account a nonlinear effect when the upper soil is not, it doesn't have any resistance to the pipe deformations, because only this part of soil resists to the piping deformations, but this one is not. That equations also doesn't take this into account. It's just a very simple equation that can be used for just hand calculation, and also it doesn't take into account the effect of the insulation around the pipe. For example, if you have polyurethane insulation around the pipe, and for example, if you have expansion cushions, special flexible cushions around the pipe, this code doesn't take it into account. It just offers some approximate method how we can consider that. But START-PROF use much more accurate method. It used the finite element model to calculate the stresses for the pipe under the soil pressure load. So here you see the iteration process. It used nonlinear model that take into account the soil pressure, that take into account the nonlinear effect of internal pressure, the pressure stiffening effect. This is the geometrical nonlinear model. And also it take into account the soil resistance around the pipe. So it put a lot of springs around the pipe. And if springs are compressed, it is taken into account. But if a spring is stretched, it has tensile stress. So this spring is switched off. So here we don't have any springs because that's switched off. Here you can see the non-working springs, and here the working springs. So all this is done automatically. So you see in this area, during the iteration, we see how some springs are switched off during iterations. Let me run again. You see here some springs switched off. So this model is much more accurate for ring bend and stress calculation. START-PROF use it automatically to calculate the stresses for this component, this one. And all other stresses calculated as required by the code. There is nothing special in it. Okay, so also START-PROF allows you to calculate the allowable wall thickness, the wall thickness required for FRP material. Let me show you how to do this. You just select File, New, All Elements, and select here ISO, this one. And here you see the wall thickness calculation. So you can define some diameter, some temperature, linear thickness, top coat thickness, chemical resistance factor, safety factor. For loading, I recommend to use 0.5 value for wall thickness calculation to have some reserve of the wall thickness. Also, we should define the service life and select material and define the pressure. After we click Analyze, let me check. Oh, sorry, 30 years. And let me run analysis so we can calculate the required minimum wall thickness of the FRP piping. Okay, so I think I've finished. So if you have some questions, please, you're welcome. You can switch on your microphone and ask your questions. Santosh, can participants turn on their microphones or not? Is it allowed?
Sorry?
I'm waiting for questions, but I'm afraid that maybe participants can't turn on their microphones.
Yeah, no problem. I think they can ask the questions. You can see a chat box. There is a question.
Yes. I just switch on the chat. I see some questions. Can you share the presentation? Actually, yes, I can share the presentation, but let me show you. One moment, please.
We can share the recording.
Yes, you can share the recording. Let me show you just a moment. I will show you the website. And here, this is the PASS Suite website. And here is the trainings, on-demand trainings. This is the training course. You can download the training agenda. This is the training agenda. Here you can see complete online pipe stress analysis course for underground piping modeling, stress analysis, and also static and rotating equipment modeling, expansion joints, and also non-metallic piping analysis. So this training course is very cheap. It is just 30 USD. And if you will participate in this course, you can download all the presentations, including the same as I just showed you. This is the presentation from this training course, but in this training course, I explain everything like I did right now, but in much more detailed explanation. Here you can find it. So I recommend you to participate in this course if you want to know more about the pipe stress analysis, including the non-metallic piping analysis. Here is the agenda. You can download it and see the website. It's passsuite.com, and there trainings, on-demand training. And also, of course, we'll share the recording of this webinar. Santosh will share view this recording. Okay, so let's see.
There are a few more questions.
Yes, I see we have more questions. What about the stress analysis of HDPE piping? Actually, in START-PROF, you can select the HDPE piping. Let me show you. I will select the first file that we created. Here you can specify the PE 4710, for example, material. But you should, if you want to analyze any other material, you should add it into the database. For example, here I added PE 4710, this material, and I calculated its properties using this Excel file to be able to perform this analysis using the DVS code. Okay. Another question, is it possible to do the underground analysis for a seismic event? Yes, we have analysis for the seismic event, and also I described this in our training course. Let me show you the help system, application guide, modeling approaches, loading. This is the seismic wave propagation. START-PROF allows you to analyze buried piping for steel piping or plastic piping, fiberglass piping analysis for the seismic wave propagation. The problem is that, for example, if you analyze the above ground piping for seismic effects, we apply the inertial loads caused by the masses, the pipe mass multiplied by the acceleration. We have the inertial load, and we analyze the piping applying that type of loads. But for underground piping, there is no vibration because pipe is surrounded the soil. But we have another problem. It is the soil deformations when waves traveling, the seismic waves traveling around the soil. We have several types of waves: P waves, S waves, Lowe waves, Rayleigh waves, and it causes the deformation of the soil, and also it causes deformations of the piping inside the soil. So START-PROF can perform such analysis, and also you can learn how to perform such analysis in this training course. I also recommend, because I explained it in great details in this training course. Okay. So let me read another question. Let me check. Underground. Okay. Yes. However, how to calculate the local stress for HDPE piping? For example, you can if you can find some code. For example, it can be NM ASME NM 0.3. From the top of my head, I'm not sure, but it is NM 0.3 where you find the allowable stresses, when you can define it here and find the characteristic parameters for characteristic equation to perform this analysis using the DVS code. Also, in next version of START-PROF, we'll add NM code, ASME NM codes for FRP and plastic piping analysis, and you will also have the alternative analysis method. If you need more detailed explanation, you can just write me on email, and I can explain it in more details how to do this using this Excel file. The next question: do we have composite materials in software database? From composite materials, we have. Let me show you. We have that manufactures that type of materials. But if you have another material, you can just add your own material, fill the properties, and you can use it. What about the small bore pipe stress analysis? It is not a problem. You can just define the small pipes and just perform stress analysis. There is nothing special in it. In general, due to the manufacture of FRP, we can have different thickness and mechanical characteristics of the pipe and components. How can we take into account START-PROF SIF if we have, for example, the straight pipe with 6 millimeter thickness and elbow with 8 millimeter thickness? Actually, you can define the wall thickness of the band. For example, here we have the straight pipe wall thickness 6 millimeters, but for the band you can define 8 millimeters, and START-PROF will calculate stress intensification factors based on this value. So this is not a problem. Another question: at the junction between straight pipe and elbow, of course, yes, it will be taken into account also in junction point between elbow and straight pipe. How to validate loads on support? Actually, I didn't understand the question. What do you mean? How to validate? If you want to just calculate the loads on the supports, you can just create a piping model, run analysis, and then check the support loads. If you mean how to do this manually, you can do this for simple models, but for complex model, it is not so easy. Okay, for complex model, you have to create some finite element model and use some software. Is it possible to perform stress analysis for non-metallic piping on Scissor 2? Actually, there is no, as I know, I am not the author of Scissor 2. You can ask Scissor 2 developers, but there is no any special methods for analysis of non-metallic piping in Scissor 2. I don't know them. It has the ISO code for fiberglass analysis, of course, but my opinion that in START-PROF we have more easy and more how to say more easy way for analysis of such piping systems from the end user point of view. But I don't know if Scissor 2 have some thermoplastic piping analysis methods, because it requires some codes, some equations, but there is no such special codes for plastic piping analysis, polyethylene piping and other. And also the main problem in Scissor, I can tell you, the problem is that Poisson ratio depends on the temperature, but in Scissor you can't define the Poisson ratio for different temperatures. There is only one value. You can input only one value. And another problem is that it depends on the material properties, depends on service life and temperature. It is also, I don't know how to define it in Scissor. It is very complex, not so easy. Maybe you will have to create several files to perform such analysis. It is not so easy as in START-PROF. Okay, so how to model different expansion joints, discharge of rotating equipment. So actually this question falls out of the subject of this webinar, but of course you can define different types of expansion joint, and also you can learn it in my complete pipe stress analysis course that you can find here, and it is on the Udemy, udemy.com. And I explain it in great details. Right now I can just tell you that you can define different type of expansion joints. It's angular expansion joint, torsion, ball joint with friction, different type of axial expansion joint, it's slip joint, expansion bellows, it's a lateral expansion joint, universal expansion joint, custom expansion joint. So you can define, and it's quite easy. I recommend you to enroll my training course, the complete training course. It's about 35 hours of content. So you can find everything there, including rotating equipment and expansion joints. And also the next question, is it possible to do hot taping on FRP pipes? How could this software help to evaluate stresses? Actually, I can just say that START-PROF can analyze the hot tap, but it is not so easy. Usually we explain it in for users of our software when user ask us in technical support, we explain how to perform the hot tap analysis. Actually, you need to perform some special load cases and create some special model, but of course software can do this. And next question, why is the thermal expansion factor almost X2 is compared to the steel pipe? It's not X2, it is X20, so it's 20 times greater than for steel piping systems. That's because the let me show you the database. For example, polyethylene 100, and here is the expansion factor. It is 0.0002. Okay, so we have 3 zeros. And now let me open the steel piping. For example, ASME B31.3. And for steel piping, it is 1 per 10 in power of 5. Okay, so it is 20 times greater. So the plastic piping material has 20 times greater linear expansion factor. Sorry, not factor. 20 times greater linear expansion factor, and of course the elongation is 20 times greater. It is L by alpha. Alpha is thermal expansion, and multiplied by the temperature difference. So the elongation for this pipe with the same length, the same temperature for the plastic material will be about 20 times greater than for steel piping, and that's why we should perform the deformation analysis, the displacement analysis for such piping system to avoid the problems like this one, as I showed on this picture. Caesar cannot perform plastic piping. Yes, maybe yes. I'm not so familiar. You better ask the developers of that software. Okay, so okay, I see another comment. Alex, thank you. I know very well your courses on Udemy, and is one of the best for sure, the best explanation of courses and detailed on FRP, and not only. the most easy way to have the load cases in START-PROF. Yes, thank you. Thank you. Okay, so if you don't have any other questions, we can finish this webinar. Thank you for your attention.
Yeah. Thank you, Alex, for your time and explaining wonderfully like how to handle the non-metallic courses. I mean, non-metallic pipings. So we will look forward for a few more interactions on the technical in the future. Thank you. Thanks for your time. Thanks all of you for attending this webinar. Recording will be shared shortly. Thank you.
Yeah, thank you. Bye-bye.
Thank you. Bye.
Thank you.